Okay, so we're going to finish off probability. We've got 2 more days. Actually, it finishes off the course too, right? And they deal with and probabilities. Okay, so we did or probability, which is the union, right? A union B, union is the U shape. And now we're dealing with A intersect B. So with an or probability, which we did, that's associated with mutually exclusive events. And that means one thing is happening. We draw a card and we want to know, is it a king or a spade, right? But we've only done one thing. We've drawn one card. In a conditional probability, we're using the word and. Conditional probability, well, when you say something's conditional, then it depends on something. So we call these dependent events. Because it's an and, it's events, there is more than one event. Okay, so if you're trying to decide, do I use an or do I use an and? You ask, is it one thing happening? Is that thing mutually exclusive, or is there more than one thing happening? So with dependent events, there's more than one event. Okay, so, well, for us, it's going to be 2, right? There'll be 2 events. A phrase that will often be associated with dependent events is the phrase without replacement. So you draw a card, and then without replacing it, you draw another card. That has to trigger within you something about, then it depends on what you drew for the first card. That'll have an effect on what you draw for the second card. Or if you have a bag of marbles, and you draw a marble out of the bag, and you don't put it back in, and you draw another marble, then depending on what happened in the first event, which color marble you got, that will affect what happens with the second event. Okay? So we've got 2 events. We're not replacing. So those events basically have to be the same thing. It has to be draw a marble, draw a marble. Draw a card, draw a card. Okay? It's got to be something like that. And you'll see without replacement. And then tomorrow when we talk about independent events, we'll talk about how do you figure out, are these dependent or independent? I'm doing an and probability. And probability goes with dependent, but and probability also goes with independent. So how do I figure out which one? Okay, so let's take a look at an example. Let's do marbles in a bag. Okay, so let's say I got a bag and I've got some marbles. And I have 2 red marbles. 2 red marbles, and I have 3 blue marbles. Actually, wait, I want 3 reds and 2 blues. Okay, I have 3 red marbles. So a bag of 5 marbles contains 2 blue, 2 blue marbles, and 3 red marbles. In a bag of 5 marbles. And what I want to do is work out different probabilities when I draw a couple of marbles, right? So, if we say, well, what's the probability of drawing a blue marble? So what's the probability of drawing a blue marble? 2 out of 5. Okay, so the probability of drawing a blue marble is 2 out of 5. So probability of blue, and the probability of red, what's the probability of red? Are there any choices besides blue or red? No. So this will be 3 out of 5, right? What do those add up to? 5 out of 5, which is 1, right? Which means we've taken into account all possibilities. There's no green marbles or black marbles in that bag. Okay, so I can draw a marble from the bag. The bag. And let's say that I drew a red marble. Okay, so we drew a red. So what's the probability of getting a blue marble now? 2 out of 4, right? Which also reduces to 1/2. What's the probability of getting red? Two out of 4. So if I draw a red marble, my probability of then drawing blue changes, right? Because now there are still 2 blues, but there are only 4 marbles left. If I drew a red marble, and I want to draw another red, there's only 2 red marbles left out of 4. So what if, then the other choice is, of course, go back to the initial. So initially, let's say initially. Okay, what if we initially draw blue? Then I'm going to have this situation. So now what's the probability of blue? Thanks. That's a remarkable. Usually it's kind of red-green colorblind. Okay? So, because there's 1 blue marble out of 4. What's the probability of a red in this case? 3 out of 4. So, let's deal with the situation where this happens. We're going to draw 2 marbles. So we're going to set up a situation where we're going to draw 2 marbles. We're not going to replace them. And we just want to see what's going to happen, right? And we're going to do this. We'll draw out a tree diagram to show this, right? And we'll just show each condition. So we're going to kind of combine what we have here. So here's the initial condition, and we have 2 blues, and we have 3 reds, and if we draw a marble, whoops, it could be a blue marble, or it could be a red marble. What's the probability of drawing a blue marble? Out of this bag, probability of getting blue is 2 out of 5, right? Okay. And what's the probability of drawing red? 3 out of 5. Okay. If we drew a blue, then we have 1 blue and 3 reds. If we drew a red, then we have 2 reds and 2 blues. So this was the first draw, right? Now in the second draw, we can have 2 possibilities, right? We can draw blue, we can draw red. So we could draw blue, we can draw red. What's the probability of drawing blue up here? 1 out of 4. Man, I'm even drawing pictures here, so we could do this without the pictures, right? So I'm drawing you a picture here. Okay, if we draw blue, what are we going to have left? We're going to have 3 reds left, right? If we draw red, what are we going to have left? We're going to have a blue and 2 reds. What's the probability for this red here? From here, it's probability of getting that red.
Oh, the
3 out of 4. Okay, now let's do the other two cases here. So again, we could draw blue. And what's the probability of drawing blue here? 2 out of 4. Or we could draw red. What's the probability of drawing a red here? 2 out of 4. And what are we left with? So if we draw blue, we got 1 blue here, and if we draw red, we got 2 of those. And we'll have 2 reds left here. We'll have 1 red left here. Okay, so, sorry?
You have one too many.
yeah.
1 too many.
3/4.
On the second,
3/4. The second.
second from the top, right there. That down, yes.
Yeah?
We should only do 2.
Oh, right, okay. So let's fix it. Damn it. Okay. Go away. Okay. So what we're looking at is a diagram of what's inside the bag, right? Using our X-ray vision. So we started with this bag with 2 blues and 3 reds. We drew a marble. If it was blue, we know there's a 2 in 5. Probability is 2/5 of drawing blue, and this is what we're left with in the bag. Probability is 3/5 of drawing red. This is what we're left with in the bag. If we drew a blue, then the probability of drawing another blue is now 1 out of 4. Depends on what happened the first time, right? If we drew a red, the probability of drawing a blue then is 2 out of 4, and so on, right? So what we do is we traverse each branch of the tree, finding the probability of, so the probability of blue followed by blue, so probability of blue and blue is 2/5 times 1/4, okay, which is 2 out of 20, okay, which reduces to 1 out of 10. The probability of drawing a blue and then drawing a red is 2/5 times 3/4, which is 6 out of 20, or 3/10. The probability of drawing a red followed by a blue, and remember, a red followed by a blue is different from a blue followed by a red. Okay, so in this case, we say the order really matters in which these things are going to happen. So the probability of getting a red then a blue is 3/5 times 2/4, which is 6 out of 20, or 3 out of 10. And the probability of drawing a red followed by another red is 3/5 times 2/4, which is 6 out of 20, or 3 out of 10. And what do all these guys add up to? 10 out of 10, or 1, right?
At the top it says B and then B. What's the symbol?
B and B, that was just the word and. So,
Oh, it's
yeah, let's just use word. We'll use our words and not the formula. So, probability of getting a blue and then a blue is 2/5 times 1/4, 2 out of 20. So probability of getting 2 blues is 1 out of 10. The probability of you ending up with a red and a blue will be this combined, right? It'll be 6 out of 10. You'll have to combine these two. If we don't care about order, right? Just wonder, what do you end up with? End up with 2 reds. What's the probability of that happening? Well, red followed by red is 3 out of 10, right? Okay, because the first red, you've got a 3 out of 5 probability. The second red, you now have 2 out of 4, right? Depends on what happened on the first draw. So this leads us to probability for dependent events. Okay, so using mathematical notation. Yeah, new page. The probability of A and B, I'm going to use the word first, and then we'll so that's using and. You're going to see with the symbol, which is the intersection, right? So it's the probability of A intersect B. And we've got one new piece of notation here, right? Which is this B, and this is a vertical line, right? So slash means minus. You're not going to see a slash on the diploma, right? They're not going to use that notation. So if you see something, it's going to be B vertical line A. So this is read as given, that little slash. So this is the probability of event B given that event A has occurred. Which is probably misspelled, but you can spell occurred anyway. So it's the probability of event B given that event A has occurred. Okay. So the probability of A and B, or A intersect B, is the probability of event A. That's easy to figure out, right? I mean, you just count how many are favorable for event A and what's the total number, times the probability of event B happening given that A has happened, right? Which means it usually changes something. There's one less marble in the bag, right? I'm not drawing from a bag of 5 marbles now, so my denominator usually goes down in this case, right? Actually, my denominator always goes down in this case, okay? Because dependent events means you're doing the same thing. You draw a card, you don't put it back, so your first probability is something out of, if you're drawing from a full deck of cards, what do you get? Something out of 52. You don't put it back, your next probability will be something out of 51, okay? So with dependent events, this formula, dependent events, you're doing the same thing, but you're not replacing, right? So you will see the words without replacement or something to that effect. The denominator is going to change for the second event. It's going to go down by 1 because you have one fewer, whatever, card, one fewer marble in the bag, etc. So how about, what's the probability of drawing 2 kings from a deck? So probability of king and king. And by that I mean the first card is a king and then the second card is a king. Okay, now for us we use intersect, right? So it's the probability of a king times the probability of a king given that you got a king. So what's the probability of getting a king? 4 out of 52. How many kings are left in the deck? And how many cards are left in the deck? So the probability of getting a king, given that you got a king, is now 3 out of 51. If this were the probability of getting a king and then a queen, then this would be 4 out of 51, because there would be 4 queens, right? So we've got 4 out of 52 times. Now the denominator is always going to go down by 1. In this case, the numerator did as well, because we're dealing with the same rank. Okay? And that works out to some number. 1 out of 221. Okay, any questions to this point? All right, now the formula can be rearranged, right? So the formula can be rearranged to solve for any of the above, right? I mean, I could isolate P of A by dividing both sides by this, but more likely what we want to do is we want to isolate this and say, hey, what's the probability of B given A? So what would the formula look like if I wanted to write it as the probability of B given A? What would that be equal to? Which you're going to have to do for sure on the test. Yeah, so the probability of A intersect B divided by P of A, right? We just got to get rid of this. So we're going to, by that, we got to get rid of this, so we divide both sides by this, and that's what we get. So the probability of B given A is the probability of A and B divided by the probability of A, okay, or the intersection. So let's say we had this situation. Try and leave this here. 70% of your friends like chocolate ice cream. And 35% like chocolate and strawberry. What percent of those who like chocolate also like strawberry? Okay, so you do a little survey, right? Flavor ice cream. So 70% of your friends say they like chocolate ice cream. And 35% like chocolate and strawberry. And we want to know what percent of those who like chocolate also like strawberry. So we set it up like this, right? We want the probability, I'm just going to leave that form where you can sort of see it. So the probability of chocolate given strawberry is the probability of chocolate and strawberry divided by the probability of chocolate. Okay, so we're matching up the formulas, right? In this case, B is chocolate given that you like strawberries. The probability that you like chocolate given that you like strawberry is the probability of chocolate and strawberry divided by the probability of just chocolate, right? Now you can't reverse these, right? You can't do it this way because you have to look and say, well, what information do I have? I know the chocolate and strawberry, and I know the chocolate. So putting this as strawberry then chocolate and reversing these and then putting probability of strawberry, that doesn't give you, because you know, maybe they like vanilla or something, or some other flavor. Okay, so now we can fill in. The probability of C given S is the probability of chocolate and strawberry, which is 35%, divided by the probability of chocolate, which is 70%. And what's that work out to? One half or 50%. Okay, so the probability that you like chocolate and also like strawberry is 50%. Here's another example. Okay, so you're off to play soccer and you want to play goal. You're going to play soccer and want to be goalkeeper. But it depends on who's coaching. Okay, so there's a couple of coaches that alternate. Depending on who's coaching, you have a different chance of getting to be goalkeeper. So with Coach Sam, probability of being goalkeeper is 0.5. And with Coach Alex, the probability of being goalkeeper is 0.3. And so you want to know, what's the probability today? What's the probability that I'm going to be goalkeeper? Oh wait, hang on, one more piece of information. Sam is coached more often. Coach more often. 6 out of 10 times. Okay, now that information. We want to know what's the probability that you're going to be the goalkeeper, right? So we can do this using a tree diagram. Okay, so what is the probability? Of you. So it depends on who's coaching, right? And then depending on who's coaching, you have a different probability. So we can work this out quite nicely with the tree diagram, right? So we can say, well, you got Sam as the coach, or you got Alex as the coach. If Sam is the coach, there's a 0.6 chance of Sam being the coach, right? 6 out of 10, which means 4 times out of 10, or 0.4, Alex is the coach. If Sam is the coach, then you have a 50% chance of being keeper. So let's just say yes, no. So being keeper, you have a 50% chance. If Sam is the coach, and it means you have a 50% chance of not being the keeper. If Alex is the coach, then you have a 30% chance of being keeper, right? 0.3. And if Alex is not the coach, then you have a 0.7. We follow the tree and we work out the different probabilities, right? So we just multiply it together, right? The probability here is 6 out of 10 chance, so 0.6 times 0.5, which is equal to 0.3. So one thing to keep in mind when you're doing probabilities, if you're doing an OR probability, it's always greater than any of the individual probabilities, right? Because you say, well, it could be A or B, right? So we add them together, we get a larger number than either of them. If you're doing an AND probability, it's always smaller because two things have to come together, right? So both things have to happen. And your chance of not being keeper is 0.6 times 0.5, which is 0.3. If Alex is the coach, then your chance of being keeper, is 0.4 times 0.3, which is 0.12. And not being the keeper is 0.4 times 0.7, which is 0.28. So what's the probability that you are the keeper? If we did this right, this should add up to 1. Does it add up to 1? Right, because these are the only possibilities. Either Sam or Alex, or either the keeper or not. Okay, it adds up to 1, right? We got 0.6, 0.72, 0.8, 1.0. Adds up to 1. What's the chance of being the keeper? 0.42. Yeah, 0.42, right? Yes, these are the yeses. So you have a 0.3 chance of being the keeper with Coach Sam. You got a 0.12 chance with Coach Alex. So the probability of being the keeper is 0.3 plus 0.12, or 0.42. Okay, that's your probability of being the goalkeeper today, right? And then all of these probabilities have to add up to 1. You don't need to do a tree diagram, right? It's conditional probability, it's dependent events, so the probability of Sam being is 0.6, and then the probability of being the keeper given Sam, right, is 0.5. Okay, so you could do that, but you have the two that you have to work out, right? You'd have to work out the probability with Sam being the coach, the probability with Alex being the coach. It's a little bit nicer this way, right? It lays everything out. You know that all your numbers are there, that they all add up. They add up to 1, which means that I took everything into account, and I'm interested in I'm going to be the keeper. Okay, so we just add those two together. Okay, what else do we want to do? We want to... All right, so we've looked at conditional probabilities. We've looked at dependent events. We did that. Okay, we've looked at rearranging the formula to solve for the probability of A given B. means we've pretty much done it all. So now it's time for you to do it all.